And we have seen that in intrinsic semiconductor, okay, we have N is equals to P is equals to Ni, okay, and Ni itself is a function of temperature. So if I write Ni as a function of temperature, we have seen this comes out d T power 3/2 exponential minus Eg upon 2 kBT. Okay, so this was intrinsic carrier concentration. Okay, this is your intrinsic carrier concentration, which depends on band gap and as well as on temperature. Okay, now we are going to calculate next important property. Okay, the position of Fermi level in intrinsic semiconductor. Okay, so I want to calculate now what is the yes. Am I audible?
Yes, sir.
Yes, sir.
Okay, so now I'm going to calculate the position of Fermi level. Okay, position of Fermi level in intrinsic semiconductor. Okay. So in order to calculate the position of Fermi level in intrinsic semiconductor, again I want to use the thing that the concentration of electron in conduction band is equals to concentration of holes in valence band. Okay, and I know the concentration of electron in conduction band is given by NC. Okay, exponential, what is XC minus EC minus EF upon KBT, and concentration of hole in valence band is given by NB exponential minus EF minus EB by KBT, where NC and NB are also constant, okay, whose value depends on temperature. So we also know what is NC and NB, okay, they're constants, so we can put their values here also. So I want the position of Fermi level. Okay, so what I can do, I can calculate NB by NC. Okay, because NB is the number of state, okay, in valence band, and NC is the number of states in conduction band. Okay, so generally NB is higher than your NC. So in order to get log positive, I am taking NB by NC. So this will be my exponential minus EC minus EF by KBT. Okay, and if I divide this one, this will be exponential minus EF minus EB upon KBT. Okay, and this is what, this is my NB upon NC. Now if I solve this, okay, so this implies this is minus EC plus EF. If I send this one, this become positive. Okay, positive, that means your EF will be also positive. Okay, and EB will be also positive. Okay, so if I write this exponential, okay, so I can write exponential minus EC plus EF. So minus EC plus EF. Okay, and if this whole will go in positive, this will become EF and plus EB. Okay, this become plus EB upon KBT. Okay, equals to NB by NC. Okay, now just with a little bit calculations, okay, I can write now what my, so if I take minus common, okay, so this become, now you can send log there. I have
सर
2EF, हाँ
माइनस ईवी नहीं होगा?
माइनस ईवी आना चाहिए, सही, माइनस ईवी आना चाहिए, माइनस ईवी आना चाहिए, ओके, क्योंकि ये ऊपर जाके प्लस हो जाएगा तो माइनस आ जाएगा, ठीक है, माइनस ईवी और EF प्लस हो जाएगा, ठीक, तो 2EF, ओके, minus EC plus EV, okay, this become KBT ln NV upon NC, okay, and if I solve it further, this give me 2EF, okay, this give me EC minus EV, just check it whether I'm doing correct or wrong. So both are minus, na? Both are minus. So both are minus. So this will become EC plus EV. Okay, EC plus EV. Okay, and this is your by 2. So I get 1 by 2 KBT ln NV upon NC. Okay, now I can remove this EF here. Now I know what is NC. My NC is 2 into 2 pi Mn star KBT upon H square, isn't it? And my NV is 2 into 2 pi MP star KBT upon H square power 3 by 2. Okay. So if I put these values here, it will give me the position of Fermi level in intense semiconductor. So I get the position of Fermi level. Okay. Like EC plus EV by 2. Okay. And if I put the value here, so I get half KBT ln MP upon Mn star power 3 by 2. Everything will cancel. 2 pi KBT H square, everything will become cancel. Only you have Mn power, MP power 3 by 2 and Mn power 3 by 2 will be left. So now I can write this is like EC plus EV by 2, okay, and this come ahead, so 3 by 4 KBT ln MP, okay, upon Mn, okay, so this is my position of Fermi level in intrinsic semiconductor. Now if you carefully look, okay, and so this comes out almost the middle of the band gap, okay, if I say this is my conduction band edge and this is my valence band, okay, top of the valence band, and say if I say this is my EG is the band gap. So if I say if MP and N are equal, then this becomes log 0, so you got EC plus EB at, if EF you get EC plus EB by 2. Okay, suppose ES is 30, suppose 10 electron volt, and this is say 2 electron volt, so then 10 plus 2, this will be 6 electron volt, so somewhere it will come here exactly in middle. Okay, actually there should be reference level from where you're measuring, so we can define the reference level also, how we're defining here. So for the moment, if I take KBT value, is KBT value at room temperature, if I take KBT at room temperature, so this comes out 1.38 into 10 raised to power minus 23 joule per Kelvin, and if I take room temperature equal to 300 Kelvin, okay, and if I convert this value into electron volts, okay, so this comes out around 26 milli electron volt, okay, or 0.026 milli electron volt. Now this 0.026 milli electron volt is very less at room temperature. If you compare the band gap, say one electron volt or 2 electron volt, 3 electron volt semiconductor, okay. So compared to this band gap value, this KBT value is in milli electron volt. Okay, so this is very is negligible. Okay, so you can say this value compared to this value at room temperature, this value is negligible. This temperature, this is around 26 milli electron volt. Okay, and then 3/4 is there, and if you the MP and M1 value, they are not very different. So in that case, this contributions comes very small. So you can assume that your Fermi level in internal semiconductor is okay, is almost middle of the level, almost at room temperature. So I call it like position of Fermi level in internal semiconductor, because internal semiconductor, so I can put here I here. So this is almost middle of the semiconductor. This is your conduction band and this is your valence band. Okay, now you can also see if so if your temperature, if you write T is equal to 0 Kelvin, okay, so this term becomes 0. So your EFI again comes exactly middle, okay, by 2. Similarly, if you say if MP is equals to Mn, effective mass are same, then also you come at ES plus EV by 2. Okay, so that means I can consider or I can assume that the position of Fermi level is almost mid of the band gap. Okay, so you can say position of Fermi level lies, okay, mid of the band gap. Okay. Now I can also define a reference level. Reference level का मतलब क्या है? Suppose this is my someone mic is on, someone mic is on. This is my EV, okay, and this is my position of Fermi level. Now I can say my Fermi level is, valence band is 0. Okay, so I can find the position of Fermi level with respect to Fermi level. Okay, I can say this is my reference level. I am calculating value from here. I can calculate value from vacuum. I can assume my value from here. So in this case, if I calculate my EF, whose mic is on? So if I calculate EF minus EV, okay, that comes out what? EC minus, if I cancel by EV, this comes out EC minus EV by 2. Okay, and what should I write? Plus KBT 3/4 ln MP upon Mn. Okay, so EC minus EB is what? EC minus EB is your band gap. So you can also say my EF minus EV is equals to EG by 2 3/4 KBT ln MP star upon Mn star. Okay, so with respect to the position of Fermi level with respect to your valence band. Okay, similarly I can calculate the position of Fermi level with respect to conduction band edge. Okay, so if you want to calculate value with respect to conduction and bench, so you can calculate EC minus EFI. Okay, so EC minus EFI, this gap, this distance, how below it is. Okay, so how below it is, then so compared to EC EFI. So if you calculate, okay, so again you will get EC minus EV by 2. Okay, and minus 3/4 kBT ln MP upon Mn. Okay, so you can write Eg by 2 minus 3/4 kBT ln MP upon Mn. Okay. So this was your position of Fermi level with respect to your valence band and your conduction band. Okay. Now what I know carrier concentration of intrinsic semiconductor, and I also know that what is the position of
Sir,
Fermi level. Ah,
sir, EFI, can you just repeat, sir, what you have just told? EFI
EFI
minus
is
EV means position of
EFI minus
Fermi level with
with
respect to
respect
valence band.
to valence band.
Okay.
Okay.
So how it is submitted with
Hmm?
valence band?
I'm calculating EFI minus EV, na? So I'm calculating this gap. This
Yes, sir.
gap
Yes, sir.
I'm calculating means I'm calculating the position of this with respect to this. Okay.
Okay.
Okay. Now I am in the situation, okay, that we are ready now to calculate the conductivity, because we have conductivity mainly depends on two factors: mobility and your intrinsic carrier concentration. So now electrical conductivity of intrinsic semiconductor. Okay. Now I want to calculate how conductivity depends on temperature. So I know that conductivity is equals to any mu. Okay, any mu n. If it is only electrons, if there are holes, I can write conductivity, general expression for conductivity as a me p e mu p. Okay, because there are electrons and hole as well. Both will contribute to the conductivity whenever I apply electric field. Okay, so electric field, so electron will move opposite to the applied electric field, and holes will move in the direction of electric field, but the current direction will be both same, so both will contribute in the conductivity. So now for intrinsic case we have n equals to p equals to ni. Okay, so I can write my intrinsic conductivity as ni e, okay, mu n plus mu p. Okay, now I already know the temperature dependence of ni. Okay, if I want to calculate this is the formula for electrical conductivity. Okay, if you know ni e mu n mu p, you can calculate the electric conductivity. If you want electric conductivity as a function of temperature, then you should know what is ni, how ni depends on temperature, and how mobility varies with temperature. So ni already we know, we already calculated dt 3/2 exponential minus Eg upon 2 kBT. Okay, and there are some constant Ni here, E also there. Now what about mu n plus mu p, whether they are temperature dependent or not? Mobility. Okay, so mobility is also temperature dependent. Okay, mobility is what? Mobility means when you are applying electric field, okay, how fast your charge carriers are moving, that is velocity per unit electric field is called your mobility. Now how mobility depends on temperature? Okay, so let me now see the variation of mobility with temperature. So if I plot mobility versus temperature plot, okay, this temperature comes out like this. Okay, so this is your, if you increase the temperature, mobility decreases as 1 by t power 3/2. Okay, and if I go at low temperature, my mobility increases as a temperature of 3/2. Okay, this is your higher temperature, and this is very low temperature. Low temperature means this frozen temperature, 10 Kelvin, 20 Kelvin, 5 Kelvin, very low temperature, okay, almost near to 0 Kelvin. So at very low temperature, okay, your mobility increases, but at high temperature, okay, and slowly at high temperature it get decreases with temperature. Now this decrease in mobility at high temperature is due to lattice vibrations, due to lattice vibration. You can say lattice vibration or phonon scattering. Okay, so when your electron is moving in the system, okay, if you increase the temperature, the lattice vibration amplitude get increase, and when lattice vibration amplitude increase, okay, so what happens, your conductivity should decrease, because now you have a more scattering. Lattice vibration amplitude, lattice vibration amplitude is high, okay, so lattice vibration amplitude high means now there is a more probability of scattering of electron. So if scattering is more, obviously it will collide, electron will have a collision, and once electron have more collisions, that means of course its drift velocity will decrease, okay, when you're applying same electric field, okay, and collision temperature, because the temperatures of more collisions are there, then your average velocity, which is called drift velocity, of course it should be obviously should be lesser, so your mobility should decrease at higher temperature. So that part is understood, okay, as you increase the temperature, so let me write here, okay, as you increase the temperature, as at high temperature, okay, at high temperature, at high temperature means anything above room temperature or usual temperature, not about, we are not talking about this freezing temperature, okay, so at high temperature, and we are interested conductivity at only high temperature, okay, because low temperature your intense semiconductor is insulator, so there you want any conductivity. So whatever conductivity generally we are interested in internal semiconductor, we are interested at high temperature. Okay, so about 300 Kelvin. Okay, 400, 500, 600 Kelvin. So there mobility only decreases. So this part is not important for us, but we can also explain this one. So this is because of lattice vibration. Okay, lattice vibration, lattice scattering, and the lower part. This is about impurity scattering. This is because of impurity scattering. Okay, so in if you have a system, okay, which has a impurities, okay, and impurities are charge impurities, no? Impurities always charge, okay, so if charge impurities are there, then what will happen when your electron is moving in the system, okay, so there is a, suppose there are you have a positive impurities, okay, some impurities are there in the system, and if electron is moving, so what, when electron is moving and it's moving very slowly, so there is a more probability of scattering. It can, if it is moving very slowly at low temperature, then it can have a scattering with this ion, okay, while if it has a little bit more velocity, the probability of scattering is less, okay, so as you increase the temperature in the beginning, okay, its mobility slightly increases, not very high, okay, it is slightly increases because the impurity scattering decreases, okay, so at high temperature you have lattice scattering, increase lattice screening, increase lattice scattering, lattice vibration scattering of lattice vibration, or phonon scattering, phonon scattering, okay, while at low temperature, what happens at low temperature, you have a reduced, increasing temperature, have increasing temperature reduced, so increasing temperature reduces the impurity scattering, reduces the impurity scattering. So when scattering is reduced, okay, your mobility should increase, okay, so this is the temperature variation of mobility. Now we are interested only high temperature, so this lower part we are not interested in internal semiconductor. This will come in picture when we use extrinsic semiconductor. Okay, now let me
So 1 minute, sir.
huh
1 minute, sir.
okay.
Okay, sir. Done, sir.
Okay, now let me write again the expression for conductivity. Okay, so we have conductivity. Okay, then we have just now written, we have b t power 3 by 2. Okay, ni, and we have of course one constant eb also, e exponential. Okay, minus eg upon 2 kbt. Okay, now I can write here, say some constant mobility also depend on temperature, so say some constant c by t power 3 by 2. Okay, mobility, because now we are not bother about a low temperature mobility, so this will cancel out. Okay, and I can simply write, this cancel out means because they will cancel out each other effect. So in the expression you just will get conductivity, you can write constant, and you can write this is exponential minus eg upon 2 kbt. Okay, so this is the expression for conductivity of intrinsic semiconductor. Okay, now if I plot this curve, if I take log of this curve, okay, so
So
what it will
what
give
is
me,
so what is sigma 0?
this
Sigma
some
O.
this constant. Okay, this constant e b, any other constant c. Okay, it includes this constants. So sigma 0 is constant. Okay, sigma 0 is constant. So whatever coming in the expression constant, that combined give a new constant sigma 0. Okay, now if I take log was sigma I, so it will give me what, minus eg upon 2 kbt. Okay, and some other constant, log sigma 0, it will give you some other constant, say a. Okay, so this is the equation of what, line. If I say this is y, and I say if 1 by t is 1 by t is x. Okay, so this is a equation of line. Okay, with varying which with negative slope. So if I plot this eg sigma conductivity versus conductivity, intrinsic conductivity sigma I ln sigma I versus 1 by t graph. So I should get a straight line with a negative slope, and the slope of this graph should be equals to minus eg by 2 kb. Okay, this is my slope, eg by 2 kb. Okay, this is my 1 by t scale. So if I calculate, if I plot my graph, if I measure conductivity at different temperatures, and if I plot as a function of 1 by t, and if I calculate the slope of this graph, I can measure the band gap of intrinsic semiconductor or band gap of semiconductor. Okay, so based on this, you have questions on exam. Let me solve one problem. So one problem came in exam. Okay, so where they have given you log sigma I versus 1 by, instead of 1 by t they will turn, now the scale is 1000 by t. Okay, and they have given you some values. They have given you some values, like they say this is 36.5. Okay, this is 34.5, and this is your 32.5. Okay, and this is say 2, this 30, and this is say this is 3. this they given this graph, so they asking what is the band gap value, what is EG. Okay, so we can find the band gap, okay, because we know the slope of this graph should be equals to minus EG upon 2 kb. Okay, so from there we can find the value of EG. Okay, so let me first calculate the slope. Slope is how much it comes? Slope will come this one, y2 minus y1. Okay, slope is what? I know only this x, this y, and this x. So y2 minus y1, that is 36.5 minus what? 32.5 and 2 minus 3. So this slope come negative, and this should be equals to minus EG upon 2 kb. Okay, and this should be 2 by 3 because here scale is 1000 by t. So this is basically not 1 by t. This is 0.003, 0.00. This is 0.002, and this is your 0.003. Okay, because scale is multiplied by 10. Actually, it is less. Okay, so this is 0.002 and this is 0.003. Now, if you solve EG from here, okay, you find the value of EG. So this minus minus will cancel. So you have 13.6, you get 4. Okay, you get 4. 4 into and 2 kb, so you get 8 kb. 8 kb, okay, and divide by how much? 3.3 minus 1, 1, and you have also 10 power minus 3. 10 power minus 3. Okay, now you solve this one and tell me how much is coming. So, and you have to convert, of course, this is an electron volt. So if you want to convert this in electron volt, so I should get EG, okay, 1.38 into 10 raised to power minus 23. Okay, of course, this is 10 raised to power minus 3 is here, and then you have to divide by 1.6 10 raised to power minus 19. Okay, so tell me how much is coming. So this is 322. So 1 power will be left here, and solve this one. This should come around 0.69, or some variation may be there, electron volt. Okay, check me and tell the answer. And slope, there was EG by 2, na? EG by 2. So have I written? Yes, I also included 2 in this 4. Okay, check it, how much is coming.
0.69, sir.
Okay, 0.69. So that is the answer. Okay. Now this is your intrinsic part finished. Now same thing we want to calculate now. Carrier concentration in extrinsic semiconductor. You want to calculate the fundamental position in n-type and p-type semiconductor. You want to understand what is the formula for conductivity for extrinsic and what is temperature dependence. Okay. Now the next part is extrinsic semiconductor. So extrinsic semiconductor. Okay, so first we want to understand carrier concentration in extrinsic semiconductor. I told you that carrier concentration is extrinsic semiconductor is high compared to intrinsic semiconductor at room temperature. Okay, the room temperature extrinsic semiconductor show electric conductivity. So why it is so? And we have discussed also that when there is a extrinsic semiconductors are 2 type. Okay, n-type. So extrinsic semiconductor are 2 type, n-type, and then we have a extrinsic semiconductor, we have p-type Okay, so when we dope fifth group element, okay, doping is fifth group element like arsenic. So arsenic becomes donor, okay, and it gives one extra electron in the system. Similarly, when you do third group doping, okay, like aluminium, okay, then you get extra hole in the system. So I told you, if there is a conduction band and here is your valence band, and say this is an n type of semiconductor, okay, so n type has a donor level here somewhere here, okay, and this donor has a, here we have donor atoms, n number of donor atoms, nd, capital D, nd, okay, nd, n number of donor atoms. So these at room temperature, these donors get ionized. So four atoms get ionized, you get 4 electrons here, or 5 ionized, you get 5 electrons here. And there's a possibility that this electrons which are valence band, okay, they can also come here. So if one is coming, you get one hole here. So if I want to write what is my carrier concentration in the conduction band, okay, so number of charge carriers n, so n is simply what? So I can write the concentration of electron in conduction band, okay, of n type material, okay, I will write by, this is nn, concentration, n is the concentration of electron conduction band. So it's n type material, so I'm writing nn. So concentration of electron in n type material, what I can write, I can simply write this is equals to nd ionized atom, okay, plus how many holes are present here. Are you getting? If suppose 2 holes are present here, so this 2 electron go here. So if I want to count how many atoms got ionized, suppose here we have 10 atom. So 10 atom ionized means 10 electrons here. And similarly 2 electron go from here to 2 holes here. So I have total how many? 12 electrons here. Are you getting? अगर मेरे पास, if I have a 10 atom ionized, so this 10 atom will give it, each will give you 1 electron. So I have 10 electron here. Okay. Similarly, there is some possibility the electron can come here from here also. Suppose 2 electrons are coming, so you have 2 holes here. So 2 holes give you 2 electrons, and 10 ionized give you 10 electrons. So you have total 12 electrons. So you can say that I have an nn equals to nd plus p. Now this contribution I told you, this number is very less. This number is very less compared to this number, ionized atoms. Okay, so I can simply write my concentration of electron conduction band is number of ionized atom. How many atoms are ionized? Okay, and how many atoms are ionized? Okay, so if I assume fully ionization means I told you above 100 Kelvin of room temperature, okay, almost all atom get ionized. Okay, so even your room temperature you can assume, okay, you can assume that all the atoms are ionized. So you can write my concentration of electron is only due to my nd, how many atoms I am doping. So each atom will give you 1 electron. So if suppose I have a 10 raised to power 10 atom doping, okay, 10 raised to 1 mole, I am doping 10 raised to power 10 atom. Each atom will give you 1 electron. That means now in conduction band I have a 10 raised to power 10 electron. Jitne, the number of electron is equal to number of atoms, doping atoms. Okay, assuming full ionization. Okay, if the question they say 50% ionized, then you can take nd plus and nd plus equal to 0.5 nd, okay, nd by 2, but I'm assuming the full ionization. Okay, so this is assuming full ionization. So assume full ionization, so I can simply write my nn is equals to nd, number of electron in conduction band. Okay, now if I want So in n-type material, in n-type material, in n-type material, okay, what I can write, the number of conduction electron Nn should be equal to my Nd. Okay, this is number one thing. Now I want to find number of holes present in n type of material. How many holes are present? Okay, so if I want to calculate how many holes are present, so I can take use of law of mass action. Okay, so what law of mass action says? So I'm erasing this one. Okay, so law of mass action says, law of mass action says that np equals to ni square. Okay, or you can also write, you're writing this for n type material, so you can write npn is equals to ni square. Okay, so I know nn, I can calculate pn. So if I want number of holes in valence band of n type material, okay, so that will be simply pn, and pn will be what, ni square upon nn, and nn I told you is equal to nd, so ni square nd. So this is pretty simple. If you have know how many atom you are doping, so you can find how many electron can come in conduction band. Once you know how many electron can come in conduction band, you can use law of mass action and you can find how many holes are in the valence band. So now you have a complete information about carrier concentration in n type of semiconductor, isn't it?
So
Okay.
what was Ni? What was Ni?
Ni is the intrinsic carrier concentration. Ni, so you will be given a semiconductor, okay, and its intrinsic carrier concentration will be given, and plus doping concentration also will be given in the question. Okay, so Ni is your intrinsic carrier concentration. Okay, even though semiconductor is extrinsic, but extrinsic, how do you making? You're making by you doping only intrinsic, and host only you think you're doping there. Okay,
Sir,
so
in n-type, number of holes is less as compared to
number of holes.
electrons.
So number of holes is of course very less compared to your nn. Okay, so in n type you can write nn is, okay, greater than nnp. Okay, or nd is, you can write nd is greater than number of np, pn, this is what pn. Okay, number of holes in n type is less compared to no. So this is a majority charge carriers. Okay, you have a, this is a majority charge carriers, majority charge carriers. Okay, now similarly I can write in p type material, in if it is a p type material. Okay, so similar argument, similar discussion what we had here.
Sorry,
I can
sir. I have a question of this. One
huh,
question also.
huh,
When we are taking number of holes in the valence band,
yes,
that was only that was same as the intrinsic carrier concentration.
hmm.
That should be same because
No,
number
okay,
of electrons in the conduction band is due to that donor atom. But
hmm.
holes, number of holes in the valence band is not due to that was
That's good question.
previously.
Let me explain you. This is you're asking this one. Okay, so you're saying here you have dopant atoms, okay, which is ionizing. Okay, so 4 atom ionizing, you're getting 4 electrons here. Okay, so this is here, this is the n concentration of electron in conduction band. Okay, and this is p, how many electrons are in your that valence band. Okay, so what I can write now, So this I can write what? Say this is my electrons. Okay. So now suppose one electron is going here. So I got total 5 and this become one hole. Now you say this Pi should be equal to Ni, isn't it?
Yes, yes.
Okay. So if I want to write my now N, okay, N is like Nd plus I am writing number of holes P. Okay. So you can write this Nd. You can also write this is Ni. Okay.
Sir, in P-type, this except
Ah,
it is
huh.
near to balance
What?
band, na?
Wait. Okay. So I can write this also Ni. Okay. But Ni, I told you the carry constant that depends on temperature. Okay. So what we get, we should have high temperature. Okay. But uh, at low temperature, we know, so we have to know Ni is a function of temperature. Okay. If I want to write here at what temperature I'm talking, and at that temperature what is the Ni. Okay, and of course your nd will be greater than your Ni. Okay, so here also you can leave this Ni here, nd here. Okay, because intrinsic and this carry constant is high only at high temperature. If your temperature is low, it is very small. Okay, even in room temperature it is small. So when it is small, you can avoid, you can reduce, you can leave out this thing. Okay, so your n is again equals to nd, isn't it?
Sir, in the law of mass section, what will we
Huh?
take it? How
Huh?
will we take it? In the law of mass section, where
Law
we
of
have taken.
law of mass action, that is I have not derived here. Okay, so that is valid for all type of semiconductor. Okay, not only for intrinsic semiconductor. Intrinsic semiconductor, we have n equals to p equals to ni square. Okay, and this is ni, so I can say it's n pi square. But here what you have is here nd. Okay, you have nd which is greater than ni. Okay, and you have p, you are saying that is what, that is what should,
That should be equals to Ni, no?
you should be equal to Ni. Okay, but again depends on temperature also. Okay, here also we cannot take this Nd and this is a Nd. How many atoms are ionizing? Okay, so that is basically, if you derive this formula, then only you can understand how it is coming here. Okay, so I have not derived here. So for the
Okay, sir.
moment, you just understand that this is the general expression. Okay, this is general expression.
Okay, sir.
Okay, so this is valid for both intensing and extensing. Okay, if you derive this one, then you can, and then you can shine the more information the how it is same. Okay, basically it depends on generation rate and recombination rate. So whenever there is a semiconductor, okay, always some electrons are getting generated and electrons are coming here in lower scale. They also recombination. So when we take this in equilibrium, this recombination rate, okay, generation and recombination rate equal, then for that we can derive this formula np equals to ni square. So this is general formula. Okay, so this you have to take approximately this is valid. Okay, so while calculating carrier concentration n type material, we will use this general formula. Now the detailed derivation of this concentration nd I have done in my material, or you have this class material. There is a, you can find a little bit detail derivation of what I have done here. Okay, so here I'm just writing the formulas. Okay, so you have n is equals to nd. Okay, and pn, you have ni square upon nd. Okay, this is for n type. So this is for n type. This is for n type. Okay, now if you similarly, if you take for p type material, so in p type material I can write the number of holes. Okay, the number of holes will be equals to ionized acceptor atoms. Okay, and that I can again take number of acceptor atoms. Okay, assuming all the atoms are ionized. Okay, so assuming complete ionization, so assuming complete ionization. Okay, assuming complete ionization, and I can find the number of holes Okay, number of holes in p-type material, number of electrons in p-type material by using this formula Ni square. Okay, so Np Pp. Okay, so it's a p-type material, so Np Pp should be equals to Ni square. So from I can find the number of electrons in p-type material equals to Ni square upon Pp. Okay. So you know now concentration of both electron and holes in extrinsic semiconductor. Okay, so let me give one problem. So he says, shall I erase this one? Okay. So it gives a germanium semiconductor. Okay, so you have been given a germanium sample. Okay, this is an interesting sample, and that has a charge density of, that is in intrinsic carrier concentration is given. Okay, intrinsic carrier concentration is given 2.4 into 10 raised to power 19. Okay, and it says the material is made extrinsic with doping, iridium doping, and the iridium doping is one atom per 4 into 10 4 is to 10 is to power 8 germanium atoms. Okay, so this is your doping. Okay, so for each this much atom they are doping one atom. Okay, and they say if there are total germanium atoms, Ng is 4.4 into 10 raised to power germanium. Okay, power 28 atoms, germanium atoms. Okay, so find the ratio of Ni versus Np. Find the ratio versus Ni versus Np. Okay, Ni is what? Ni is intrinsic carrier concentration. Okay. So here Ni is intrinsic carrier concentration and Np is what? Now when we are doping iridium, In, that is we are making is p-type material. Okay, we are talking is making p-type of material. So Np is number of electrons in p-type of material. So of course earlier you have Ni. Okay, now Ni when you make it p-type dope, so my number of holes will increase and number of electron will decrease. So this ratio I need to find out. So earlier how much electrons were there in the intrinsic, and later after doping how much electrons are in there in p-type material. Find, calculate how much is coming. So how can you calculate? How should I calculate? So first I need to calculate what is the doping. What is the doping? Okay, the doping is p-type. So what is the concentration of dopant atom? What is the Na? Because it's a p-type iridium atom, so p-type doping. So they're saying they are putting one atom in the host crystal, okay, per this much atom, and total atoms are this much. Okay, so how many impurity atoms are there? So impurity atoms are there 4.4 into 10 raised to power 28 divided by 4 into 10 raised to power 8. Is this correct expression or not? Let me know whether it is correct
So
or not.
once more, can
Yes,
you
sir.
explain, sir?
See, ये पूछ रहा है कि कितने एटम डोप.
How
हाँ.
do we know it's p-type?
Huh? But they are saying EDM atom. Okay, so whenever you dope EDM is a EDM is +3, so it will give you p-type material. Okay, so
Okay, sir.
EDM impurity is given in the question. Okay, and one atom per this much atom. So total this much atom, so how many atom will be doped? Okay, so I can calculate the concentration of Na. So once I know Na, so in p-type material, if I want to holes, so my holes are assuming complete ionization. Okay, in question the complete ionization is not given. Okay, so not given, that means you can take they are not given partial ionization. Okay, so you can assume that all the atoms whatever they get ionized. Okay, so pp will be equal to Na. Okay, number of holes in p type, or what they are asking number of electrons in p type. So we can use law of mass action. So if you want number of electron in p type, that will be simply Ni square upon Na. Okay, and they finally they are asking the ratio of Ni upon Np. Okay, finally they are asking ratio of Ni upon Np. So Ni is your 2.4 to 10 raised to power 19, or let it be, say this is Ni, so let it be Ni, and here you have Ni square upon Na. Okay, so Ni cancel, power cancel, so finally you have left with Na upon Ni. Okay, now what is Na? Just now you calculated Na was how much? 4.4 4.4 28 divided by
4
4,
into 10 power 8.
and this is Ni is what? 2.4 into 10 raised to power 19. Now you can see also here. Okay, your Na is greater than Ni. So calculate how much is coming. Solve this one and tell me what is the answer. Four point five eight. 4.58. Okay. 4.58. Okay, is the correct answer. You can check it. This is 19. This is 8. 27. So you will left with only one power here. This has become 44. Okay. Now 44 divided by 4, 11. 11 divided by 2.4. How much is coming?
It was 4.4 or 44?
Which one? It was 4.4. 4.4 into 10 raised to power 28. This is 4.4. Okay.
1.1 divided.
Okay. आना चाहिए चेक करो.
आ रहा है सर.
Okay. So any questions for today's doubt? Okay, that was good question she asked, that how can we say Ni equals to this law of mass action. Okay, how can we take, once we are saying one is greater than, so if I saying number of holes. Okay, so that for the moment, okay, we are not doing that derivation. Okay, that we are not going that much depth. Okay, so you just remember that this is valid for law of mass action is valid for external semiconductor also. Okay, we can derive this from, we can derive also. Okay, if you want I can send you the derivation also. Any other question?
Thank you, sir.
Okay, so I'm stopping, I'm leaving. Okay, thank you very much.
Thank you, sir.